So, good afternoon. My name is Manuel Firmino, and you are all welcome to the 5th Creativity Talks. This initiative was started by the Department of Informatics Engineering of the Faculty of Engineering of the University of Porto and organized with the Faculties of Fine Arts, Humanities, Psychology, and Educational Sciences, among other institutions. We expect these talks to cover several scientific and artistic areas, discussing and studying creativity, helping to promote a proactive attitude in our students and in general in our lives. Each talk will also feature a guest moderator that will in his turn present our keynote speaker, which we are very honored to have today, Professor and researcher Edward Lee. Our moderator, Miguel Carvalhais, is a designer, musician, and assistant professor with habilitation at the Faculty of Fine Arts of the University of Porto. He studies creative practices with computational systems, having written the book Artificial Aesthetics on the topic. His research and practice explore how computational and procedural systems are read by humans and how procedural discovery and interpretation are paramount for the creation of meaning and the aesthetic experience. His artistic practice spans computer music, sound art, live performance, audiovisuals, and sound installations. He runs the Chronicle label for experimental music and sound art at the XCOAX conference on computation, communication, aesthetics, and X. Please, Miguel.
Thank you, Firmino. Hello, everyone. I'll be moderating today's session, and right after the talk, you can send us, or during the talk, you can send us questions via the YouTube channel, and I will then relay them to Professor Lee during the Q&A. But before that, let me introduce Professor Edward Ashford Lee. He's a computer scientist, he's an electrical engineer and an author, and currently the Robert S. Pepper Distinguished Professor Emeritus in the Electrical Engineering and Computer Science Department at the University of California, Berkeley. Edward Lee studied at Yale, MIT, and UC Berkeley, and he also worked at Bell Labs in the 1980s for a while. During his career, he wrote several textbooks, as well as 2 books for more general audiences, both published by the MIT Press. The first one in 2017 was Plato and the Nerd, the creative partnership of humans and technology. And more recently, last year, he published the Coevolution, the Entwined Futures of Humans and Machines. As it's clear from both titles of these books, creativity, both human and machinic, is one of his very deep interests and one of his research focuses. So Professor Lee's talk today will be based on this most recent book, The Coevolution, and it will cover deep neural networks and artificial intelligence, as well as applications to natural language processing, image classification, and other fields such as self-driving cars. He will also, I think, address explainability in AI systems, their predictability, and their capacity to surprise their users and creators, and how, because of these non-deterministic behaviors, deep neural networks can maybe lead us to a plausible model of machine creativity. So after this year of talks in this creativity cycle, this talk, I think, will be a perfect closing to the program, or to this year's program, of really exciting talks on creativity across domains and applications. So thank you very much for being here, Professor Lee. We're incredibly honored to have you, and I'll give you the floor. Thank you.
Thank you, Miguel. That was a very flattering introduction. I'm really honored to be here. I'm fascinated by this series of lectures. I think it's really quite a wonderful thing to be pulling together this kind of multidisciplinary view of technology and creativity. So it's a real pleasure, and thank you for inviting me. So let me just begin with explaining that, as Miguel mentioned, what I'm going to be talking about is largely based on these two books that I published fairly recently, the Coevolution just last year in the middle of the pandemic. And there's also these books have led to a bit of follow-on work. I've got a paper draft that's under review. It's a bit of a new experience for me because it's actually being submitted to a psychology journal, which I have never published in psychology journals. And so I think it's not very likely to be accepted, but I'm happy to share drafts of it if you send me email. And I think that it really goes into quite a bit more depth than the books on the topics that I'll be talking about today. So in the Coevolution book, there's a chapter in that book on accountability. And the question that it's addressing is, at what point does an artificial intelligence earn the requirement to hold it accountable for its actions? That's the question that chapter addresses. And that problem, of course, is a very practical problem. As we're deploying self-driving cars, for example, who do we hold accountable for accidents? But I started addressing the question by asking, when do we hold an AI accountable for its creativity? That's a very difficult question. So there's a very interesting backstory behind this. So this is a picture of Pierre Fautrel, who's a member of a small group of French artists who call themselves Obvious. And they created what they billed as the first AI. Well, they claim they didn't create it. They claim that this painting, this portrait of Edmond de Bellamy, is, according to them, the first purely AI created artwork. In this book, The Coevolution, I address this question of when should we hold an AI accountable for its actions, and start with the question of when can we give it credit for its creativity. So anyway, this group, Obvious, put this portrait of Edmond de Bellamy up for auction at Christie's, and Christie's expected to get maybe $7,000 to $10,000 for it, and it eventually sold for $430,000, to the tremendous surprise of everyone involved. Now, the question here is, who is the artist? So let me give you a little bit of backstory on this. So the name of the painting, Edmond de Bellamy, is a hat tip to this person, Ian Goodfellow, who is the inventor of a style of deep neural networks known as generative adversarial networks. And Bellamy in French basically means good friend and good fellow. So that's how they picked the name of this. It's sort of a hat tip to this inventor of the technology that they used to create this painting. Now, what was driving Ian Goodfellow's work in generative adversarial networks was an effort that was quite active in the AI community, still is actually, to create synthetic images that are credible, as that they are competitive with natural images. And there was a project at Google that was attempting to do this called Deep Dream. And the way that they went about this was that they would train a neural network to recognize certain kinds of images. So for example, you train a neural network to recognize dogs in an image. And when the neural network is being trained, it's got hundreds of thousands or millions of parameters that are being tuned as it goes through the training data set. And these parameters are varying as it's learning to recognize an image of dogs. So what the Deep Dream project did was they then took the neural network that had been trained to recognize an image of dogs, and they turned the algorithm around so that when they feed it an image, instead of tuning the parameters, it would tune the image to try to make the image match what it thinks a dog-like image should be. So the same algorithm was being used, but in a rather different way. Instead of tuning the parameters of the neural network, it was tuning the pixels of the image. And so, for example, if you started with this image of jellyfish on and ran it through a neural network that had been trained to recognize images of dogs, after a few iterations, you would get something like this. After a few more iterations, you would get something like this. And these are really quite striking images. And in some ways, I think quite artistic and provocative, but they're not very natural images of dogs. And so to some degree, even though, this might create some rather disturbing and compelling images, they weren't accomplishing the goal of creating synthetic images. So Ian Goodfellow figured out that you could play off neural networks in an adversarial game where one neural network is trying to synthesize images and the other one is trying to discriminate between synthetic images and natural images. And you set them off to play against each other in trying to do this. And eventually the neural network that is trying to synthesize natural images gets much better at synthesizing natural images. So Pierre Fautrel and the other artists at Obvious took this technique and unleashed it on a large collection of images of portraits, and then used this generative adversarial network to try to synthesize new portraits that would be based on the ones that it had been trained on, but would be genuinely synthetic portraits. So they used software that was written by Robbie Barrett, who was then a high school student. He then went to Stanford to study, but Robbie Barrett himself is an artist and was using his own open source software to generate some really quite striking artistic images. This image on the left, for example, is based on a training set that used artistic images of nudes as its basic training set. And so Robbie Barrett is really quite an artist in and of himself, and he was using these generative adversarial networks, and he built this software that was then used by the group that calls themselves Obvious to generate this portrait of Bellamy. So how do we assign accountability to that portrait now, right? In fact, the group Obvious really didn't make very big changes to Robbie Barrett's code. So is Robbie Barrett the one we should credit for the portrait? Or is the portrait really the creation of an AI? An AI like this will actually generate a large number of images, and you have to select among these images. And so there's a selection process. So is the AI really more of just like a better paintbrush? Is it a tool that's being used by an artist to select among results? And of course, there's a long history of artists actually performing more of a selection than creation process, right? One of the most famous examples of this is Marcel Duchamp's found objects, right? This is declared an artwork by Marcel Duchamp. Now he didn't create this urinal, right? So is the found object among the synthetic images created by this AI actually the artistic creation? So this accountability gets kind of gnarled, and in my opinion, the actual artwork that was created and that sold for $430,000 was a piece of conceptual art. It was the idea of a first AI created artwork. And what was presented as the physical artifact is really potentially validly viewed as a found object, not as a creation of the artists who are Pierre Fautrel and his colleagues at Obvious. So this fits very well with the tradition in modern art. And it's a perfectly valid, I think, a perfectly valid interpretation, and it takes away the creativity from the AI. The AI really was just a mechanical thing that was producing a selection of objects for the artist to choose from to create this piece of conceptual art. Now, this interpretation, I think, is a valid interpretation, but not the only interpretation. So I think that Margaret Boden has, I think, articulated this interpretation of the use of AI technology in art very clearly, where she says AI techniques can be used to create new ideas in three ways: producing novel combinations of familiar ideas, exploring the potential of conceptual spaces, and making transformations that enable the generation of previously impossible ideas. So in particular, you know, that image of the jellyfish turned into dogs, that would be really hard to come up with. And you could argue that that's a previously impossible concept. And then, you know, when you select an image like that out of a large number of images that are created by the AI, perhaps you are really using the AI as a tool to create artworks. So I think this is a valid interpretation, but it's not the only interpretation. And I would like to actually focus the rest of the talk on a different interpretation and a much more difficult question. And the question that I would like to focus on is really, at what point can an AI actually be the creator and be the artist, right? What would it take to get to that point? Now, let me give a little bit more of a backstory on this. So you probably all remember Deep Blue, the program created by IBM that beat Kasparov in chess in 1996. Now, this was before the current machine learning revolution. So this was what people call a GOFI design, good old-fashioned AI. It was a pretty brute force solution to the chess playing problem. It was doing combinatorial search of the large number of possible moves that were departures from any particular state of the chessboard and selecting the best among those large possible number of moves. But Garry Kasparov wrote a very interesting book after this event of having been defeated, where he argues that contrary to expectations, this emergence of machines outdoing the chess masters didn't actually kill the game of chess. In fact, he argues that it actually has enriched the game of chess. That human chess players are actually learning from the machines, and they're learning more about the game of chess, and they're learning interesting things that they can do with the game of chess. So that interpretation now suggests that there's something that the machines are bringing to the table that is more than just a tool, perhaps. Now, in the modern era of deep learning, you can go quite a bit further. So AlphaGo, as you know, defeated Lee Sedol at the game of Go in 2016. And the interesting thing about this is that the brute force techniques, the GOFI techniques used by IBM to play chess, are actually not viable for the game of Go. The number of possible moves is astronomically larger than it is for chess. And we don't have the computer technology to do the exhaustive search that can be done with chess if you have enough resources. But with Go, it's not within the technological possibilities to use that kind of solution. So DeepMind, which was then acquired by Google, who created this program, used these generative adversarial networks that Ian Goodfellow had developed. And they essentially set the AIs to play an adversarial game against each other. And they would try to defeat each other at Go, They're given just the rules of the game and nothing more. Now, DeepMind claimed at the time, I'll read you a quote from their press release, right? The creative moves it played against the legendary Lee Sedol in Seoul in 2016 brought completely new knowledge to the Go world, while the unofficial online games it played under the moniker Master, earlier in the year have influenced many Go's leading professionals, including the genius Jia himself. Events like this week's Pair Go, in which two of the world's top players partnered with AlphaGo, showed the great potential for people to use AI systems to generate new insights in complex fields. This really, I mean, you can take this however you like. I mean, this is a press release, right? It's an advertising statement, but it is, I think, an interesting perspective. And I think that Go masters, I'm not a Go player, so I can't comment on this, but I have read some Go masters who have studied this particular game in 2016 against Lee Sedol and found some of the moves that were made by the machine truly surprising, and moves that they would not have expected at all from a human player. And so there's something that the machines are bringing here that is different, okay? So one thing that I would like to point out is that there's another lesson from this AlphaGo phenomenon, right? There's this mantra that data is the new oil, and that AI today is all about data. Actually, AlphaGo disproves that, because the only data fed to AlphaGo was the rules of the game. They didn't feed it a long history of, recorded games of Go from which it learned to play. That's not the way the program built its expertise. The way the program built its expertise was just to play adversarial games against itself, using just the rules of the game. So the system learned to play through feedback. This notion of feedback is something that I think is really quite central, and the transformation in AI from these classical good old-fashioned techniques to the modern era of machine learning really amounts to the introduction of feedback into these systems. The feedback was missing before. The idea in good old-fashioned AI was that you could codify the decisions that were to be made by the machine as a collection of rules that reflected the expertise of humans, expertise that humans had built up over time. You just codify those rules, deductive rules, rules of logic, and you get an intelligent response to your questions. But that's not the way AlphaGo worked at all. In fact, there weren't any rules of thumb, or if you see this particular pattern on the Go board, make this move. Those rules were completely absent. Okay. Instead of those rules, you have this feedback system where the machine learns on its own by playing against itself. Now, I'm not going to talk about the technology of these neural networks, but I would like to point out, I mean, I know how these programs work, and I understand what the algorithms are in the machines that are implementing these neural networks. And a key insight that I got was that understanding these algorithms, how the machines are actually implementing these deep neural networks, gives almost no insight into why they do what they do. It doesn't give any clue. A neural network gives you some answer to a decision problem, and no matter how well you understand the software that's running, you still cannot explain that decision. So there's something rather different going on here than this kind of good old-fashioned deductive rule-based reasoning. So one way to interpret this is that the decisions that are being made by a deep neural network are not, in fact, rational. Now, what do I mean by rational here? Well, let's take a very narrow definition of rationality. Okay, and this is a definition that is really, I think, rooted for me in Herb Simon's work on rationality. So I'm going to define rationality to be step-by-step processes governed by rules of logic that maximize some utility function. So a rational decision has these characteristics. It is arrived at by a step-by-step process following rules of logic that maximizes some utility function. That's what we mean. That's what I'm going to mean by a rational decision. I'd like to contrast this with creativity, which I think of more as a continuous process. It's more intuitive than based on rules of logic. And instead of maximizing utility, it's based on this very nebulous concept of aesthetics. So this notion of rationality, as I mentioned, it really comes from, I'm borrowing from Herb Simon, and who's I think maybe the only person to have won both a Nobel Prize and a Turing Award. But in his work on the bounded rationality, one of the key ideas is that humans are actually not very good at this kind of rationality. The step-by-step processes that maximize utility for almost all interesting decision problems are not actually tractable to humans. The number of steps required is vastly more than what a human can possibly carry out. So Herb Simon's point was that humans don't actually behave rationally in this sense most of the time, because the rational process is very difficult for us. Interestingly enough, it's actually often rational processes in this sense that are difficult for humans are easy for computers. So computers can carry this out and handle vastly more complexity than humans can. So the argument that Herb Simon was making is that a lot of the decisions that humans make actually fall more on this in this category in the right, where there's more intuition involved than rationality. So this idea was developed by the psychologist Daniel Kahneman in this famous book, Thinking Fast and Slow. And Kahneman is another Nobel Prize winner. And here he makes the distinction between system 1 and system 2 in the human mind. And system 2 is the rational system. It's the system that tries to use deductive logic to come to decisions through the use of step-by-step processes that maximize utility. And that's the slow in the thinking fast and slow. The fast is intuitive, quick, instantaneous. Your brain just reacts and makes a decision, and you aren't in fact able to provide the reasons and the logic that led to the conclusion. Kahneman actually points out that humans are very good at constructing post facto explanations for how they came about a decision, that they'll give you a set of logic steps that may have plausibly led to the decision, but they didn't actually lead to the decision. The decision came about through this extremely quick intuitive process. So deep neural networks operate more like these intuitive processes. They're actually very quick, right? You give them a data that represents a decision problem, and they do a bunch of number crunching on that data and come up with a decision. And there's no rules of logic that can rationally, in this sense of rationality, have led to that decision. The steps made by the computer, which is billions of steps of little arithmetic steps, are not, in fact, a rational explanation and cannot be a rational explanation for the decision. It's useless to try to use those as a rational explanation for the decision. So the DNNs are really operating much more on this right-hand side of the screen than on this left-hand side of the screen. And in fact, the whole effort these days to try to mandate rational explanations for the decisions that the AIs come up with, I think is a bit misguided because it fails to understand this phenomenon. And in fact, I suspect that that whole agenda is going to be undermined very soon because people are going to figure out they're going to use generative adversarial networks and create AIs that can give a rational explanation for any decision. You give it a set of data and you give it a decision, and it'll give you a set of deductive rules that could have led to that decision. But those won't have been an explanation for how the AI came up with that decision. That will be much more like the human tendency to create a post facto rationalization for some decision. And at that point, I think we really have a conundrum because we have explanations, but the explanations are not in fact valid. So what about this rationality? Well, so rationality in this sense is very closely tied to the notion of computation as defined by Turing and Church that forms the core of computer science. Computation is step-by-step processes using deductive rules of logic that lead to a final conclusion, okay? Complexity of these computations is simply a count of the number of steps. This is the Turing-Church notion of computation. And so in my book, I actually talk quite a bit about the relationship between computation and algorithms, which are also these step-by-step operations, rationality and objectivity. So objectivity means that, it's just the rules of logic and the utility function that is driving the process and nothing more. There's no subjective judgment in this. Now, I would like to point out that computation in this sense is not universal. Many people misinterpret this key result of Alan Turing, where he showed that there is a universal machine, called it a universal machine. It's subsequently been more appropriately called a universal Turing machine, which is a machine that can carry out any computation of this sense that can be carried out as a finite sequence of deductive steps governed by rules of logic. It's universal in the sense that it can carry out any such processes, but those are not the only processes in the world. And in fact, I would like to argue that there's a whole family of processes that don't fit in this category. These are processes that involve interaction between a machine and its environment, that involve embodiment. So a machine inside of a robot body with sensors and actuators. It involves feedback systems. Feedback is completely absent in the Turing-Church model of computation. In the Turing-Church model of computation, all of the inputs to the system are provided at the start of the computation. The computation then goes through a finite number of steps, reaches a termination, and has a conclusion. There's no feedback in that system. Feedback systems, however, are actually significantly more powerful than computations. You can do things with feedback systems that are simply not possible with these objective, non-interacting computational systems. So in my book, The Coevolution, I use the work of 4 other Turing Award winners, Judea Pearl, Robin Milner, Silvio Micali, and Shafi Goldwasser, to show that interaction is fundamentally more powerful than observation and fundamentally more powerful than computation. Interaction requires a first-person self, almost by definition, right? Interaction means you have to have an ego self interacting with an environment. Interaction is also very much, in this case, a two-way street. It's a feedback, okay? A first-person self requires interaction. You can't have a first-person self without having interaction. So feedback, interaction, causation, free will, accountability. I argue in my book that these are all, in fact, tied together. This is a difficult and nuanced argument. It's really, it was really a challenge to construct this, and it took several chapters to construct this. And some of the arguments in my book are pretty technical. They're not presented mathematically, but they're fundamentally mathematical ideas that show at a very fundamental level that interaction is more powerful than observation and then computation. This will become of no surprise to psychologists, right? There's many people have bought into the idea that was, I think, very eloquently pushed by Esther Tellin, who really pushed this concept of embodied cognition. In her words, the mind simply does not exist as something decoupled from the body and the environment in which it resides. So in her view, and in this embodied cognition view of cognition, cognition is the interaction of the brain and its environment, its body and the environment around the body. So cognition is the interaction. So it's not something that interacts, it is the interaction. That's a key distinction, okay? And I think it's an important distinction, and it tells us a lot about whether AIs and when AIs are going to be able to actually achieve something that we might legitimately call cognition. And my claim is that an AI that has something that starts to resemble cognition will arise from cyber-physical systems, systems that interact with the physical world and are not just purely computational systems. Purely computational systems, I think, will be incapable of cognition in the same sense that Esther Tellin here says that the brain is incapable of cognition without interaction with the body and its environment. So that kind of interaction, of course, is a feedback system. It's a system where the machine provides stimulus to the environment reacts and provides stimulus back, and you get this close coupling, a dynamics that evolves. Now, this notion of feedback and the power of feedback is quite old. It, in fact, predates computation. In the 1920s, Harold Black at Bell Labs showed that these negative feedback systems could be used in very powerful ways to compensate for deficiencies in physical components. In particular, he was focused on amplifiers that were being used for telephony, for long distance telephony. And he showed that feedback could be used to take a very poor quality amplifier and get extremely good performance out of it. So this idea has been around for a while. The idea was famously pushed by Norbert Wiener, who coined the term cybernetics for these kinds of systems that are interactions of computation, control, and the physical environment. Now, I recently learned that Norbert Wiener is often credited with having developed the feedback control systems that were used in World War II automatic radar-guided anti-aircraft guns. Well, it turns out he was not really the developer of those technologies. He had a research contract as an MIT professor from the Army to develop that technology, but apparently the output from that research project was a collection of not very important, very dense mathematical theoretical papers about this, and not really the technology that was actually used in World War II. So sometimes we give people credit for things that they don't actually deserve credit for, but that's the nature of accountability. We like to single out the single artist, which is why this question of who painted the portrait of Edmond de Bellamy becomes such an interesting question. So what about creativity? How does creativity relate to free will, causation, randomness, determinism? These are not easy questions, and these are questions that I try to address in this book from from a fairly, what I think is a novel perspective. I mean, of course, people in psychology have always, and in philosophy, have tried to address these questions from the perspective of the human condition. But in my book, I'm really addressing these questions from the perspective of, can an AI have free will? So from the perspective of artistic creation, let's look at the question of determinism and free will. So this is a wonderful pair of paintings by Robert Rauschenberg. And Rauschenberg was trying to make two identical paintings using his kind of signature standard techniques, which combined, lithographic works with found objects and paint and other found media. The two paintings are pretty similar, but they're far from identical. And this, I think, was kind of a Rauschenberg commentary on the question of determinism and free will. His goal was to make identical paintings, but he couldn't really get there, okay? And that perhaps is driven by fundamental limitations. Is it fundamentally a consequence of non-determinism or randomness? Well, that's actually hard to say, because it turns out that determinism doesn't imply predictability. You can take a perfectly deterministic system in the sense, it's deterministic in the sense that given its starting conditions, there's only one possible behavior, but it is still completely unpredictable. And one of the nicest illustrations of that is due to Lewis and McGregor, who published in 2006 this beautiful thought experiment where they just looked at two spheres colliding, and they constructed a completely deterministic model of this using classical Newtonian physics. Perfectly deterministic model, set of differential equations. There's only one possible behavior. Then they looked at the question of how precisely would you need to know the initial conditions in order to predict behavior. They assumed that you would measure the initial conditions of these objects optically using a microscope or some other optical technique. And then they derived the required wavelength of light that would be required in order to predict the positions of the particles after 35 collisions. And they found that the wavelength of light that would be required was such that a single photon of such light would have more energy than is posited for the entire universe. So this would be a sufficiently small wavelength that the energy required is more than what is available in the universe. As a consequence, they concluded that even though this is a deterministic system, it is absolutely unpredictable. You cannot, through any means, determine what its behavior will be after 35 collisions. And yet nature will solve it. If you build such a system physically, nature figures out what the position is after 35 collisions. Somehow it does that, even if the underlying mechanisms are ultimately deterministic. So this phenomenon is known as chaos. And this was developed very nicely by Edward Lorenz, who was a professor at MIT in the meteorology department. They used to have a meteorology department. And Lorenz was a pioneer in the use of computers for weather prediction. And in weather prediction, the thermodynamics of weather is really quite well understood. And it was quite well understood in the 1950s when Lorenz was doing this work. And Lorenz was very frustrated by the fact that the computers were really unable to predict the weather more than a few days in advance. And he finally identified that this wasn't a limitation in either the models or in the computing. It was a fundamental limitation that the system itself was chaotic and had this property that even if it's deterministic, it is not predictable. So many people actually assume that Newtonian physics is deterministic. Well, the philosopher John Norton in 2007 published a very controversial paper that gave a very classical Newtonian system, showed that, in fact, this system could exhibit non-deterministic behavior without violating any of Newton's laws. This paper has been really quite controversial and has led to a lot of repudiations, and I've studied the problem in quite some depth myself. And I believe Norton is right that this actually does open a hole in Newtonian mechanics that allows for non-determinism. So in 2016, I developed a paper that approaches this question from a slightly different perspective. And I prove in this paper that any set of deterministic models that's rich enough to encompass Newton's laws and also allows discrete behaviors like collisions of objects, that any such set is incomplete. It inevitably has holes in it that admit non-determinism. And consequently, we're never going to have a fully deterministic model of the physical world. And non-determinism is an inevitable phenomenon that can sneak into things. So is this tied into creativity? Perhaps this inevitability of non-determinism is something that enables creativity. It's also possibly something that enables free will. So I try to tackle this problem of free will in my book. And again, this is a historical conundrum, right? In fact, John Searle has dubbed the free will problem as a scandal in philosophy because we've been working on it for thousands of years and have, in his opinion, made no progress on it. And yet it's something that we all have an intuitive understanding of and all feel is an essential part of creative processes. How can you have a creative process if you can't make choices? So the philosopher Sam Harris actually published this book where he argues that free will does not and cannot exist in any material system. And he argues that this is true whether the system is deterministic or non-deterministic. It doesn't really matter. So free will does not and cannot exist. So I try to counter that argument in my book from the perspective of, well, at what point will we have to assume that an AI is actually capable of making decisions on its own? In which case we will have to hold it accountable for those decisions. That's the key question that I address. At what point will we have to hold the machines accountable for their decisions? I take as a premise that the human body and the human brain is also a machine. And we do hold human beings accountable for their actions. So it is not far-fetched that at some point synthetic machines will also need to be held accountable for their actions. So one of the things that I do in my book is I leverage this idea of causality and causation, and in particular, leverage Judea Pearl's work, which I'll get to in a second, but let me explain what I mean by causality or causation. So these are a simple idea, that every effect is produced as a consequence of some law of nature by a cause. Okay, that's an absolutely central concept. You can't have free will without a notion of causation, right? Free will is the ability to make a decision, and that decision must have consequences, or it's not really a decision, right? So the decision has to have an effect, and the decision becomes the cause of that effect. Some evolutionary psychologists have argued that that's actually a human capability that developed as a consequence of Darwinian evolution, because it's useful in survival to understand that the actions of an organism have consequences. It would be very difficult to survive without that concept. But the core idea of causation is actually very problematic, both in physics and in philosophy. So Bertrand Russell famously in 1913 challenged this idea of causation. He said, the law of causality, I believe, like much that passes muster among philosophers, is a relic of a bygone era, surviving like the monarchy, only because it is erroneously assumed to do no harm. So he challenged the community to say, well, look, most of our physical laws don't actually use causation. Why are we using it in all our explanations? That's the essential point of his question. So Judea Pearl went much further, and he showed that you cannot reason about causality by objective observation alone. If you insist on being objective, you can't say anything about causation. That's a very fundamental limitation. You have to become subjective. He has a beautiful example in his recent book called The Book of Why that he wrote with Mackenzie, published in 2018, a really wonderful book. I recommend reading it. But in this book, he asks the question, well, if you look at school-age children, shoe size and reading ability are correlated. So does increasing shoe size cause improved reading ability? That's a question. It's a question you could test, perhaps, using statistical methods. The shoe size and reading ability are correlated, for sure, okay? But they're also correlated with age, a confounder. And if you control for age, you will find that the correlation goes away. However, you could look at celebrities from the movie industry, for example. This is Pearl's example. And you will find that beauty and talent don't seem to be correlated among the celebrities. So you might ask the question, does beauty cause talent? But then if you control for some measure of celebrity, a correlation appears, which seems to imply that if you choose to control for celebrity, you can conclude from the statistics that beauty causes talent. So the question of whether you control for celebrity or whether you control for age, according to Pearl, is not an objectively answerable question. You have to subjectively make a choice. Okay? It's not possible to do this objectively. So he also shows that to establish causation requires randomness. So you need, for example, randomized controlled trials to determine whether a COVID vaccine is effective. Okay, you have to give some people a placebo, some people the real thing, and you have to choose randomly. And it has to be random. It can't be free will by which you make the choice, because then you could have subjective judgments that are affecting the outcome. So you need randomness, actually, to be able to do this. So I'm teaching a freshman seminar that's based on my book this semester. And one of the freshmen in my class, Rebecca Bernstein, came back with what I think is an incredibly beautiful question that was, right after reading this chapter where we talk about Pearl's results. She said, if randomness is required to establish causation, and causation is required for determinism, how can you ever establish determinism? So there's a kind of a circular reasoning here that also suggests that there's a hole in this concept of a deterministic world. So can AIs be creative? Well, my claim is that creativity requires interaction, embodiment, feedback, and subjectivity, and that these are beyond the capabilities of even a universal Turing machine. A universal Turing machine doesn't have these properties and is incapable of realizing systems that have these properties. But that doesn't mean these properties are beyond machines. If our brains are machines, we have these properties. So deep neural networks, in my opinion, even though they're currently implemented on computers, are actually a first step towards synthetic machines that actually could have these properties. The fact that they're implemented on computers, I think, is an accident of history. There are implementations of deep neural networks that actually are not fundamentally using computers. There's this whole field of reservoir computing that uses very analog physical devices as a core part of the neural network. And there's a lot of innovation happening right now in machine architectures that are really quite different from von Neumann computing machines that we're all familiar with, that are being used to implement neural networks much more efficiently than what we're getting from the classical computing machines. I think we're going to see a lot more innovation in the architecture in machines, and they're going to look less and less like computers, but they're still going to be using this same principle of these deep neural networks, the thinking fast of Kahneman in a machine. It's not deductive logic that they're doing. It's not sequences of logical steps governed by logical rules. It's much more like this quick intuitive thinking of system one. So in conclusion, we have these two worlds: rationality, algorithms, computation, and objectivity. My claim is that those are not universal. The second world, interaction, embodiment, feedback, and subjectivity, can fundamentally do more than what you can do in this world of rationality. And DNNs, deep neural networks, are not fundamentally algorithmic in my claim, and they show signs of properties from the second category already. So thank you very much. With that, I'll point you again to these two references, and maybe we can open up for questions.